let's look at a different coin game. So Bob proposes a new game to Alice. So now Alice bets $1 on the outcome of a fair coin toss. And if Alice wins, she gains $2 net. And if Alice loses, she loses her $1 bet. So the game is different from the first coin game. In the first game, Alice had negative expected value. Here we're going to see that the payoff is going to be better. And so of course we'll have that question, should she play this game? And so let's look at this from the expectation analysis. So let Z represent the random variable of Alice's net result. So she's winning 2 with probability half, and she's losing 1 with probability half. So if we compute the expectation of Z is going to be equal to plus 2 times half plus minus 1 times half, which is equal to half. So 0.5. So this means that Alice wins 50 cents on average for every $1 bet she does. So unlike the first coin game, this game is favorable to Alice. And so if she could play this game many times at $1, it seems like it's a good idea, right? It seems like it's a good idea to be playing this game. But now, so that answers this question. Should Alice play this new game? It seems like yes, but we have a more subtle question now. How much should Alice bet, right? So suppose Alice is allowed to bet any amount of money she wants. So should she just be betting as much as possible? Should she bet her entire bankroll every round? So every round she goes and bets all the money that she has, right? So from the point of view of one round, that sounds very tempting. After all, if the game has positive expected value, then larger bets give larger expected winnings. But this is where looking at expected value can be a bit misleading. So let's look at this. So let's think of this from the point of view of maximizing the expected value. So let's say Alice is a huge fan of expected value. She saw before if the expected value is negative, she shouldn't play. And so for her, it's all about maximizing expected value. Okay, so let's look at what happens when she is betting a certain amount B on the game, right? So if she wins, she gains twice her bet. And if she loses whatever amount of dollars she bet. So now if we do the expectation of betting B dollars, so this is going to be the 2B times half plus minus B times half. And so this is going to be just B over 2. And so the expected net gain is B over 2. And what this means is that to maximize the expectation is same as maximizing B. Maximizing B. So from this point of view, if Alice's only goal is to maximize the expect winnings every time, she should just bet as much as possible. But now think about this. Does this look like a good long-term strategy, right? And so the problem is going to be that large bets are also going to create large risk, and that's something that is not captured when we just look at the expected value. So suppose Alice begins with some initial bankroll. So she starts with some initial money, x0 equal to B. So this is all the money that Alice has, right? Maybe $10,000, $100,000, I don't know. This is all the money that she has. And now the idea is that she goes and she repeatedly bets all her money. So what's going to happen here? So if we call xn what's the Alice's bankroll after n tosses, so what will happen is that if she wins a round, she gains twice her bankroll. So her new bankroll is her original bankroll plus twice the amount. So she ends up with 3 times her previous bankroll if she wins, which is half the time. But if she loses everything because she's betting all her money. So this is what our random variable xn looks like. And so what is the probability of Alice eventually going bankrupt then, right? So let's look at that. So Alice goes bankrupt if she ever loses once. So after n rounds, the only way she is not bankrupt is if she won every single one of those n rounds. And so let's write this out. So the probability that she eventually goes bankrupt, let's say at round n, so that this is equal to 0, is going to be 1 minus the probability that there are no losses in the first n rounds. Because again, if she loses at any time, she's going to lose all her money. She goes bankrupt. Okay, so since the probability of not losing each round is half, then this probability here, probability that she goes bankrupt in round n, is going to be equal to 1 minus half to the power of n. And so what happens when you take the limit here? So the limit of this, so if she plays too many times, the limit of this, when this goes to infinity, is going to be the limit of this expression here. And half to the power of n goes to 0, so this will just be 1. And so what this means is that if Alice keeps betting her entire bankroll every round, she'll eventually go bankrupt with probability 1. And so this is the key lesson here. The game has positive expected value. Alice has the advantage, but betting everything is still a terrible long-term strategy. So expected value is important, but it's not the whole story, right? When we make repeated bets, we also need to think about risk, bankruptcy, and long-term growth.